In 1961, physicist Rolf Landauer dropped a conceptual bomb. Information isn't just abstract, it's physical. He posited that erasing a single bit of information, changing a 1 to a 0, necessarily dissipates a minimum amount of energy as heat. This isn't a limitation of current technology, it's a fundamental law. For decades, this was theory, tangled with the famous paradox of Maxwell's demon, a tiny being that could seemingly violate the second law of thermodynamics by sorting hot and cold particles without expending energy. Charles Bennett resolved this in 1982, showing the demon must store information about the particles, and erasing this information incurs the thermodynamic cost Landauer predicted. This minimum energy, kT-ln2, where K is Boltzmann's constant and T is temperature, is known as the Landauer limit. In 2012, an experiment by Barut and colleagues at IBM directly measured this heat dissipation, confirming Landauer's principle. Deleting your browser history, that email, or even a single character literally makes your device infinitesimally hotter, and by E=m squared, infinitesimally lighter. Consider Wikipedia. If all its text data were stored using electrons, 1 per bit, its physical mass would be roughly 1.5 times 10 to the power of minus 12 grams. Trivial, yet undeniably real. Information has weight, a physical cost, a tangible presence in the universe. This physical nature of information is the bedrock upon which our entire exploration rests. Computer scientists, in their quest for efficient distributed systems, stumbled upon a universal truth and named their algorithm accordingly, the gossip protocol. Proposed by Demers and colleagues in 1987, these epidemic algorithms mimic how rumors or diseases spread through a population. A node with new information doesn't try to tell everyone. It tells a few random neighbors. Those neighbors tell a few more, and so on. This seemingly chaotic process is incredibly robust and efficient. Amazon's DynamoDB, a foundational NoSQL database, uses gossip for maintaining data consistency across its distributed servers. The Bitcoin network relies on a similar mathematical gossip to propagate transactions and new blocks across tens of thousands of nodes worldwide. Information in these systems spreads in O log n time, where n is the number of nodes, an incredibly fast logarithmic scaling. This isn't just an analogy. The mathematics describing information propagation in these digital networks is identical to that used for modeling viral pandemics or the spread of rumors. It's the physics of connection, where concepts like the 6 degrees of separation found in small world networks, theorized by Watts and Strogatz in 1998, are not just sociological curiosities, but emergent properties of interconnected systems obeying fundamental propagation laws. Information, it seems, inherently favors this viral, gossipy mode of travel when aiming for widespread distribution. The parallels extend directly to human society. Alex Pentland's work on social physics at MIT uses sensors to track human interaction, revealing that idea flow and behavioral change within organizations follow predictable mathematical patterns, much like energy in a physical system. Dunbar's number, suggesting a cognitive limit of roughly 150 stable social relationships, can be interpreted as an information processing constraint. Mark Granovetter's seminal 1973 paper on the strength of weak ties explained why novel information and job opportunities often come from acquaintances rather than close friends. These weak ties act as bridges between otherwise disconnected social clusters, allowing information to gossip its way across diverse groups. We see this in digital social networks. Data from Twitter cascades, analyzed by researchers like Del Vicario, shows that information, true or false, spreads following power law distributions, characteristic of critical phenomena in physics. Even encrypted platforms like WhatsApp don't fundamentally alter these propagation patterns, merely the observability. Facebook's controversial 2014 emotional contagion study demonstrated that emotional states can be transferred through a network, spreading like thermodynamic heat. The Shannon entropy of a social network, a measure of its information content and uncertainty, can be mathematically equated to thermodynamic entropy. A viral piece of content, with its R0 value indicating how many new people one person infects, literally follows epidemiological mathematics. Your group chat is a tiny thermodynamic system. This isn't confined to our macro world or digital constructs. The universe itself operates on gossip at its most fundamental level: quantum information theory. Quantum decoherence, the process by which quantum systems lose their quantumness and behave classically, is essentially the universe gossiping about a particle's state. The environment, acting as a multitude of tiny observers, extracts information about the particle, its position, momentum, spin, effectively broadcasting it. This forces the particle out of its delicate superposition of states into a single definite state. Wojciech Zurek's theory of quantum Darwinism, further detailed in his 2009 Nature Physics paper, posits that objective classical reality emerges because multiple observers independently acquire the same information about a quantum system, a consensus formed through this environmental gossip. The infamous black hole information paradox, which questioned whether information is lost when it falls into a black hole, finds a potential resolution in Hawking radiation, a kind of cosmic gossip where information about what fell in is subtly encoded in the outgoing particles. Biology, too, is rife with quantum and informational gossip. Horizontal gene transfer allows bacteria to share DNA directly, like passing notes in class. Quorum sensing is bacteria literally having group chats. They release chemical signals, and when the concentration reaches a threshold, they collectively change behavior, such as activating virulence or glowing. Even cancer cells spread through corrupted information, a breakdown in the body's normally coherent cellular communication. So why does information want to be free? This isn't a poetic metaphor. It's a direct consequence of fundamental physics, specifically the second law of thermodynamics. This law states that the total entropy or disorder of an isolated system can only increase over time. Information entropy, as defined by Claude Shannon in his 1948 landmark paper, A Mathematical Theory of Communication, measures the uncertainty or surprise in a message. Physicist E.T. Jaynes, in his 1957 work, powerfully demonstrated that information entropy and thermodynamic entropy are not just analogous, but are in fact conceptually the same thing. Information is a measure of order. Its spread is a move towards a higher entropy state for the system of information itself. Concentrated, unshared information is a low entropy state. As it spreads, replicates, and becomes known by more entities, the overall disorder or distribution of that information increases, satisfying the second law. Stuart Brand's famous 1984 declaration, "Information wants to be free," is thus a literal observation of thermodynamics in action. Attempts to hoard information, like digital rights management, DRM, or paywalls, are essentially attempts to fight an increase in entropy. The Streisand effect, where attempts to suppress information only make it spread more widely, is a perfect social demonstration of entropy maximization. The universe trends towards maximum information dissemination, a concept further echoed by the holographic principle, which suggests the universe's maximum information content is proportional to its surface area, not its volume, implying information is eager to reach boundaries and spread. The universe, it appears, operates like a vast cosmic game of telephone. Imperfect copying, or gossip with errors, is fundamental to change and evolution. Genetic mutations, the engine of biological evolution, are essentially transcription errors, gossip within the cellular machinery. The information in DNA is copied, but not always perfectly. These tiny miscommunications, these mutations, are then spread through reproduction. Sexual reproduction itself can be seen as a biological imperative for information mixing, a way to increase genetic entropy and explore new configurations. Richard Dawkins, in The Selfish Gene, 1976, introduced the concept of memes, units of cultural information like ideas, tunes, or catchphrases that spread from brain to brain. Memes replicate, mutate, and compete for attention, following mathematical patterns astonishingly similar to genes. Think of oral traditions. Ancient stories were maintained with surprising accuracy, not by perfect individual memory, but through communal repetition and redundancy, a form of error-correcting code built into the social transmission. Yet, variations crept in. Urban legends are a prime example of memes evolving for maximum transmissibility, shedding details that hinder spread and amplifying those that captivate. Even language evolution shows this entropic drift, with words changing meaning and pronunciation over time, driven by common usage and misinterpretations. the linguistic equivalent of gossip shaping the information landscape. If information inherently wants to spread, can we ever truly stop this cosmic gossip? History is littered with failed attempts. China's Great Firewall, despite its sophistication, is constantly embattled by VPNs and other circumvention tools. Information, like water, finds roots around obstructions. Copyright law, in its strictest forms, often fights a losing battle against the natural thermodynamic tendency of information to disseminate, especially in the digital age where copying is trivial. Classified information, no matter how tightly held, has a notorious habit of leaking, often following predictable patterns of social network propagation once the initial breach occurs. These are all battles against a fundamental force. However, we can be clever. Error-correcting codes, used in digital communication and storage, don't stop entropy, but they delay its effects by introducing redundancy, allowing the original message to be reconstructed despite noise and errors, a managed form of gossip. Cryptography is a fascinating example of using entropy against itself. Strong encryption aims to make the information content of a message indistinguishable from random noise to an unauthorized observer, effectively hiding the signal by maximizing its apparent entropy. Quantum encryption takes this further, leveraging the principles of quantum mechanics. Like the observer effect, itself a form of information gossip, to guarantee secure communication. If someone tries to eavesdrop on a quantum encrypted message, the very act of observation changes the message, alerting the sender and receiver. It's like trying to intercept a whisper that vanishes if anyone unauthorized leans in too close. These are not about stopping information flow, but directing and protecting it, working with rather than directly against the universe's informational currents. The implications of this gossip principle are far-reaching. For tech companies, it means that fighting information spread directly is often like fighting gravity. A more successful approach might involve guiding its flow or ensuring its quality. Data breaches are not just security failures, they are entropy at work on concentrated information. For governments, censorship is thermodynamically challenging in the long run. Information will find pathways, and suppression often requires ever-increasing energy and control, leading to fragile systems. Perhaps governance should focus more on fostering information literacy than on building digital dams. For physicists, particularly those in fields outside information theory, there's a call to recognize that information might not just be a tool for describing systems, but a fundamental constituent of reality itself, as suggested by thinkers like Seth Lloyd in Programming the Universe. What if space-time itself is a computational process driven by information exchange? For social scientists, the realization that they are, in many ways, studying applied physics, the thermodynamics of human interaction, could unlock new predictive models and understanding. The spread of fads, financial market panics, political polarization, these could all be analyzed through the lens of information cascades and entropic forces. And yes, even your supposedly nosy neighbor, the local gossip, is an agent of entropy, playing a small but cosmically consistent role in ensuring information doesn't remain stagnant. They are, in their own way, ensuring the local information system tends towards a higher state of distribution, however trivial or annoying the specific content might seem. It's a universal pattern, from the subatomic to the social. The universe, it seems, doesn't care much for your secrets, or anyone's. From the primordial information of the Big Bang spreading across the nascent cosmos, dictating the fundamental laws and forming the first structures, to the intricate dance of quantum particles knowing about each other, to the way your ex might be spreading information about your recent breakup, it's all underpinned by the same relentless phenomenon. We are not merely living in an information age. Defined by our technology, we are inhabitants of an information universe. Gossip, in this grand cosmic sense, isn't a social flaw or a trivial pastime. It's the universe's primary mechanism for learning, evolving, and existing. It is the engine of complexity, the driver of change, the very process by which reality coheres from uncertainty. Every shared idea, every replicated gene, every quantum measurement is a testament to information's innate drive to propagate. Privacy, in this context, becomes a fascinating struggle. an attempt to create a small, temporary bastion of low entropy in a universe that overwhelmingly favors spread and disclosure. And in the long run, entropy, the universe's tendency towards maximum information distribution, almost always wins. The question isn't whether information will get out, but how, when, and what we learn from its journey. Perhaps the most profound gossip of all is the universe constantly telling us about itself.